Okay, chapter 7. But before we get started, I have a question for you. Hypothetical. If you had a choice, if you could receive $1 million, or if you could receive a penny, but your money would be doubled every day for 30 days, which one would you choose? Now don't think about it too hard. I just sort of want your gut feeling right now. And at the end of the lesson, we'll let you calculate it. So don't even think about it. Just tell me what you think. All right. But we do want to talk about exponentials. So the idea here, let's start with parent function. In general, whenever you have a function that has a constant base, so b for base, and a variable exponent, that's an exponential. So here we have a base of the exponential. It's the thing being raised to a power. It is a constant, okay? And we're going to look in the beginning at bases that are greater than 1, and then we'll see what happens if it's not. And they're also going to remember that this exponent is a variable. So what's changing is the power. Okay, so what we want to do is we want to look at, of course, what this would look like on a graph as a parent function. So we'll start by making a table of values. And on that table, we want to have lots of values for x, some negative, some positive. I haven't really decided what the domain is yet, but I'm just going to pick some x values and see what happens. And then, of course, y is equal to, now we need to pick a number for the base. So any number will work. You know, you can pick 2 or 3 or 4. You can pick any number that's greater than 1 in this example. You can pick pi, but I'm going to pick 2 because that's going to make our life easier for this first example. So let's just go ahead and come up with some of these values. So we're just raising all of these to an x power. So in this case, y is equal to -3 is being squared. Oops, pause that. Whoops, I have not got my mind wrapped around exponentials yet. Sorry, I'm a little distracted. So let's scratch that, because that's exactly what I don't want you doing, so maybe it's good that I demonstrated what not to do. Alright, anyways, we're making a table of values, and we start with the 2. The x value is the exponent, see what I mean? So it's 2 raised to a -3. And I could figure out what that is. Let's see, that would be 1 over 2 cubed, which is 1 over 8. So I hope you can read that. That says 1 over 8. And then we're going to do the same with the other values. So we have y is equal to the base 2 raised to a -2, which is 1 over 2 squared, which is 1 over 4. Alright, see what's going on? We're making use of our negative exponents, and then we just have to raise to a power. So this one, I'm losing my row, but y is equal to 2, the exponent is -1, that's just 1 over 2. And then we have y is equal to 2 to the 0 power, but you remember anything to a 0 power is just 1. And after that, things are going to get a little simpler for us. 2 to the 1 is just 2, 2 squared is 4, and 2 cubed is 8. So we have these ordered pairs that I want to go ahead and put on the graph. Something like this. Let me switch my color. When x was -3, I have a value that's 1 over 8. So, you know, if this is 1 over 8 is really close to the x-axis, but not quite. And then I have a value that's -2 for x, and 1/4 for y. So again, -2 in the x puts me here, 1/4 puts me just above the x-axis. When I have -1, I have a half. So I'm not making a lot of progress yet, but I am getting a little bit higher. And then here I have when x is 0, the y value was 1. Okay, so I'm right there. And then I had the 1, 2 value, about there. And then I had a 2, 4 value. Things are picking up steam here. 1, 2, 3, 4. I'm up here. Okay? And then, of course, the last one that we had calculated so far, 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. Unfortunately, I'm not home in order to put, I don't have my work computer, so I can't put graph paper on this. But I think you're going to get the idea. So this curve is really, really, really steep. Then it comes down, and then it gets really, 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 really flat. Okay? So the graph looks basically like this. So this is a graph of y is equal to 2 to the x. And that's a great shape. We call that exponential growth. You're going to want to remember that shape. And we want to be able to talk about, though, some features of this. Okay? So let's talk about features. It is continuous. I'm running out of room. Okay, I'm going to put it here. Continuous. It is 1-to-1. Ah, you say. I know what that means for us in the future. Of course, it means that it will have an inverse. So, of course, we will be talking about that inverse later on. The graph, we could talk about increasing interval, would be minus infinity to plus infinity, because this is an always increasing function. Never does anything else except keep getting bigger and bigger and bigger. And then we could talk about domain and range. Let's see here. Domain. What did happen with those x values? Could we have gone to more and more x values on the positive, the right-hand side of our graph? And there's absolutely nothing stopping us from raising to the gazillion and one power. It's just take us forever. And is there anything that would stop us from taking 2 raised to the negative gazillion power? No, you're just going to get 1 over a huge number. So the domain for these is all real numbers. Okay, so that's huge. We also want to talk about range, though, because that's maybe more interesting. When you look at this, you notice the feature seems to go forever and ever up this way, and there's nothing going to stop it. It just keeps getting higher. So the y values go to infinity. But what about on the left-hand side? What is happening as we go to the left to the y values? And they seem to be flattening out. So the question is, do they ever cross that x-axis? So to cross the x-axis, that would mean you'd have to have y equal 0 at some time. Okay? So 2 raised to some exponent, will that ever equal 0? So the question, 2 to anything, will it ever equal 0? And you can think about that for a while and convince yourself that no, that doesn't ever happen. And think about what does happen as x gets huge. It's 2 to a negative huge number, which is 1 over 2 to a huge number. Are you with me? So that's 1 over a huge number. And 1 over a huge number is really small. That's just the way fractions work. So what happens is, as you go to the left, it's getting closer and closer to that x-axis, to y equals 0, but it never ever will get there. It'll just keep getting closer and closer. And that's the whole demonstration. If I, ask me to walk halfway to the door with every step I take, I'll never get to the door, okay? So we call that in math lingo an asymptote. Okay? The asymptote is a line, okay, that the graph approaches without ever touching or crossing, okay? It approaches that line without ever getting to it. So it's approaching y equals 0, or you could say the asymptote is the x-axis. All right, so that's the asymptote. So that's going to help us with our range. The range for this one, 0 okay, because it almost gets there, infinitesimally close, but we have to put the 0 with the round parentheses because it does never equal 0. And then of course it can go forever and ever, we said above that, so 0 to infinity would be a range. So those are two very important features of our exponential graph. And then the domain and range, and then we know we have our asymptote at y equals 0. And there's one other thing that we really like to focus in on, and that's the y-intercept. The y-intercept is going to be very important for us, and you'll recognize it right here, where it's crossing the y-axis, or when x is equal to 0. So we're going to write down the value of that 0, 1. All right. Wow, sorry about that 10-minute slide right there. But we don't have too much more to talk about. We're just going to talk about transformations and other things about this graph. Before we go to transformations, we're going to talk about a new kind of transformation. It's just changing that base. We had used base was equal to 2. Of course, you could make a 3 or a 4 or 5. So I'm going to remember to draw what we'd already had. There's my x, my y-axis. When I had y is equal to 2 to the x power, it came down around here, it came up, and did this little scoop where it's fairly flat on the left and then it gets really steep on the right. It went through this point right here that was 0, 1, and it had an asymptote that we would say y equals 0 is an asymptote, and we like to designate those with dotted lines. Okay, so, and it happens to coincide with the x-axis, so it's a little harder to do if you don't have a change of color. So, that was our 2 to the x. So what would happen with 3 to the x? So let's do a quick table of values. Okay, so I found my table of values. I want to put them on the graph and see how this graph differs than the other one. So when x was negative 2, I had a ninth. When x is negative 1, I have a third. A third is smaller than a half, so we are below the line right here, okay? And then we had x was 0, I have y is 1. That's where they coincide. Okay, so they both have this 0, 1 point, but over here it was minus 1 and a third. When it's x is 1, y is 3. It used to be 2, that was this one, so now I'm here. So that's the point 1, 3, and then 2 and 9. That's going to be off my scale. Oh, yeah, up there somewhere. Okay, so what's going on is I'm actually getting closer to the y-axis faster. We hit that same coinciding y-intercept, and then things get much steeper faster. Okay? So as the base is getting larger, this curve is getting steeper on the right, and it's steeper on the left because it approaches that x-axis even faster. Okay? So, you see what happens with the base. Okay, I guess we should, now's as good a time as any is to talk about what happens when that base is less than 1. We talked about base 2, we've talked about base 3, but I still want to be greater than 0, okay? But I want to talk about those bases that would be fractional. So let's imagine, if you would, that I had y is equal to 1 over 2, and that whole thing is raised to an x power. Okay? So we would go and make a table of values. Maybe I'll let you jump in on this. As I'm doing this table of values, for this one with that 1/2, all being raised to a negative 2 exponent, the negative means take a reciprocal, so this is just 2 squared, and you get 4. Okay? Again, if I had 1/2 raised to a negative 1 power, negative exponent means take reciprocal, so this is 2 to the 1, and that's just 2. Anything to a 0 power is 1, and of course 1/2 to the 1, and 1/2 squared. So let's go ahead and put those on the graph. Okay, so I didn't do so hot hitting my points, but you see what's going on is I have now what we call exponential decay. As you go from left to right, the value of y is getting smaller very quickly on the left. You're, very quickly decreasing y on the left, and then it plateaus out, it flattens out on the right this time. So everything's sort of switched left and right. Wait a minute. We've sort of talked about that before when things switch left and right. This sure looks like what we've just accomplished is what's a horizontal reflection. We have reflected across the y-axis. Compare this graph in the upper left, 2 to the x, compare that with the graph of 1/2 to the x, and they see it's a horizontal reflection. And that makes sense if you think about it in this context. What does the negative exponent mean? Well, we could have written this as 2 to the negative x power. And you see there in this context that I have a negative x instead of an x, so that means a vertical, let me get that clear, that means a horizontal reflection. We do want to point out, anytime you're graphing, you want to give at least the 2 key features, and this one is no different. What's interesting is even though we did horizontal reflection, the key features didn't change. I still have an asymptote, y equals 0, and I still have a y-intercept of 0, 1. So those 2 key features didn't move. So you almost have to sort of identify one more point to make it clear what's happening here. So -1, 2 might be good to point out for a feature. Okay, this next part's going to seem really redundant because we're talking about transformations. And guess what? We have a parent function that looked like f of x was, let's call the parent function 2 to the x, and we have a basic graph for it. Okay? And now we're going to talk about these transformations where we shift to the left and right, where we shift up and down, where we vertically reflect. We've already talked about horizontal reflection, and of course we can do vertical stretches and things like that. So it is all exactly what you would think, and we do it all under the guise of this sort of generic equation. Y is equal to A, describing the vertical stretches. Here's your b for the parent function having a b raised to the x could be shifted by h. And then we could have plus k, that vertical shift. So let me just do a couple for you. For example, what if we had y is equal to, let's do 2 to the x plus 3. Alright, when we do a vertical shift, everything goes up 3, right? Every y value. And that includes the asymptote. So don't forget to move asymptote also. Anything vertical. Okay? So I'm going to take every feature that I had on the original and just go up 3. So let me start with the asymptote. Instead of being at y equals 0, I'm going to move it up 3. And so I have dot, 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 dot. You see why we need these dotted lines? Just to help us see where the asymptote is. So y equal 3, I will label the asymptote. And then I'll start my graph. And it's going to approach. And then it's going to start its curve upward. And it goes through this point that's 1 above where the asymptote had been. That 0, 1 point moved up to 0, 4. Okay? And you could say that 1, 2 point moves up to, what would that be, 1, 6? And we could check that. When x is 1, I have 2 to the 1, so that's just 2. Oh, fiddlesticks, I blew it. Okay, I found my mistake. It's something that I do a lot, so but I found it. We're not moving up 4, okay? The 0, 4 was moved up 3 from the 0, 1, so I would have moved the 1, 2 up 3 as well, so that makes that the 1, 5. Does everybody follow? Okay, that's a vertical shift. And the same thing would happen if we went down. Make sure you're moving the asymptote down with it as well. Alright, let's look at what happens with a horizontal shift. Remember, your x's are always backwards, so what we're looking at is going to the right 4 spaces. So if I took my asymptote and move it to the right 4 spaces, I haven't moved it anywhere. You wouldn't even notice it. It doesn't move. So here we go. We're just going to put it right along, as just like it was before, along the x-axis. Y equals 0, still the asymptote. Moving left and right did not affect it. But I do need to move the 0, 1 point to the right 4 spaces. Okay, so now that becomes the 4, 1 point. So let's get that on here. 1, 2, 3, and 4. That's my new point there. And then the 1, 2 moves over as well, 4 spaces to give me 5, 2. Okay, and we have that same basic shape. It's coming down and it's approaching 0. It's often nice to identify this y-intercept. It's a nice kind of feature of your graph, and we'll talk about that and how to do that. If you want to think about it, you can. It's a good problem. But that's our transformations. We've talked about horizontal, vertical shifts. Oh, we still have to do a vertical reflection, so let's do that. So we all know if you want to talk about a vertical reflection, you put a negative sign on the outside of the function. So all of your y values become the opposite of what they had been before. Well, we had always had positive y values before. So now when you think about this, we're going to have all negative y values. But let's start with the key features of the asymptote. We had y equals 0 as an asymptote. And if I make that negative, the hit doesn't do anything at all. So again, we still have the asymptote unchanged, y equals 0. But then we had that point 0, 1, which would become 0, minus 1. And then the same thing is going on with 1, 2 becomes 1, negative 2. And you see what's going on here. I have this approaching from below the x-axis, and then it gets to the y-intercept just below, and then it takes this nosedive as it gets to large negative y values. So I still have y-intercept, but now it's 0, minus 1, and I could label this point 1, minus 2. But otherwise it's looking very familiar to us, and of course then I can combine these transformations and everything. Alright, but that's a lot to talk about. Hope you had a great weekend.